Okay, let us solve some differential equations. So in this course of our Math 3, there is a couple of differential equations that we have to solve. So the assumption that I will have is that we already know what a differential equation is because we did that in our Math 2, which was just last semester. So we definitely still remember the definitions. You can tell the order of a differential equation. You can tell if a differential equation is linear or is not linear. You can tell if it's homogeneous or is not homogeneous. So those are basics. I will simply just assume that we are still very fresh with them because again, it's just something that we just finished in just the previous course. So in the differential equation that we'll be doing here, so my focus will simply be on the technique because that is what we have now. We know what a differential equation is. So the only thing that I would say we are learning at the moment is simply just the technique to be able to solve different kind of differential equations. So the one that I'll start with, in fact, today in this recording, is a technique that we also did in the previous class. So I'll just try to focus on that, and then which is really just a revision. So I'll just show you what I'm talking about, and then I will bring in just two examples which we will just solve and finish. I don't want this recording to be long, so I think two exercises will be enough just to refresh this technique on your mind. Okay, so what do we have? So we are studying the ordinary differential equation. And now the equation that we'll try to solve today is the equation that you are able to solve using separation of variable method. Okay, so we want to refresh. Really, we are refreshing. Okay, we separation of variables. Okay, so say separation of variable method. Okay, so as you remember, just everything that we do in maths, so the problem that you are facing, it tells you, just by looking at it, it tells you what method you must use to get a solution. So when we started these differential equations, we will always have something which is called the standard form. So it's basically just how the equation look like. Then just by the look of it, you are able to actually figure out the right method to use. So how do these equations then look like? Okay, so the beginning here, it actually begins with a differential equation, which is look of this kind. It's a multivariable function on the other side. But this is actually a general structure. So this that you have here is simply just it's quite general. Because the other method that we will also discuss, it start with the same structure. The f of xy that we want for this method here is the one that we can be able to write as a function of x multiplied by the function of y here. Right? Okay, so this again is a general case. Specifically for this method, this f of xy function must be able to be written separate, like as you can see here. So that will be it. So if you are able to write this f of x y in this right hand side here as a multiplication of the two functions, then the question now is, what then must you do next? Okay, so I put this one as a key to say you can enter to these steps. Then what are those steps? So the steps that you have to do here, you simply have to separate the y variables, put them away from the x variables. So anything that is carrying the y, try to put it onto the left-hand side of the equality sign, and anything that is carrying the x and some constant, leave it, or say put it to the right-hand side of the equality sign. And that is always possible if you was able to separate the right-hand side. These variables you was able to separate with multiplication. So what you have to do now, so it therefore means we must therefore have here a 1 over v of y. Now on the side of dy dx, then the right hand side we are left with x only and some constant which may be some coefficient into the x variables. So next you have to further separate these differentials, so you must then be able to have 1 over vy dy here, then I take the dx to the other side, then you have a dx on the other side. Then lastly, what you have to do after you've managed to separate the variables like this with equality sign, then what you have to do, which is the last thing basically, you just have to integrate the right hand side, integrate your left hand side. Of course, integral with respect to y here, and then it's an integral with respect to x on the other side. So obvious, the two integrals that we see here, they do not have the limits, which therefore means they must come with the constant. So the constant according to we are integrating, so we must have constant of integration here. So instead of putting two constant, now say plus c1 on the side of y, say plus c2 on the side of the x, we normally just put in just one constant. You can always put it on the side of the independent variable, so you only have to put two c values as a c1 and c2. The range of this one c is from minus to positive infinite, so whatever sum which may be maybe sum of c1 plus c2 plus c3, etc, 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 it simply just can sit all of the sum. We can just put it all together as just one c variable. Okay, so we always just do that. Okay, so after you integrate, you would see two things. The first case is that you can get implicit function. It's not a problem. So the function that you can get in, you may find that you are getting an implicit function. It's not a problem. It is the answer. It's acceptable. Another thing that you'll see also is that you also can get an explicit function, which will be nice if this is happening, but is not always the target. So you can also get explicit function. So the two things that you may actually get. So basically, as a summary now, I'll try to do an exercise. This is what tells us we can use a separation of variables. If that is the case, this is what we get. Then we follow through with the steps from here straight down to what we get as the solution. So once you have your general solution, another thing that you may have to do is that if there are conditions that are given, say maybe there were conditions that were given here, they tell you that y is equal to some certain value, I'll say y1 for instance, corresponding to some x that we have given here. I can also say for instance x1, but just say x star is fine. So once you have these, once we have your y here, the general solution, then you will have to apply this condition. You have to apply your y value, you have to apply your x value. This will give you your c that you have here. So then this will now shift from this so large number of solutions according to the value of c into just a value of c that correspond into the values that are coming with the conditions, which then gives you a solution called a particular solution, which is a solution according to the conditions that you have given. That will be basically the last thing. Okay, so let us try to apply this technique in finding solution into these two exercises that I have with me here. Okay, make some space. So this is our first exercise. So let me write the statement. So they say here, they say solve the following. Solve the following. Let me just say ODEs. Solve the following ODEs. Then they say find the particular solution. Particular solution. Where possible. Okay, so it's a small letter P where possible. Okay, good. Let me just write both of them. So the two exercises I have, the first one is this one. So it's a ln x, it's a plus x, dy dx is equal to 0. Then they give us a condition here, y1 is equal to 2. They assume there is a statement here, say leave answer in 3 decimal places. Let me just say 3 decimals. They say leave answer in 3 decimal places. I'll just make it short. Okay, so the second exercise we have, it says y plus y prime is equal to x, y minus y prime. Okay, good. Yeah, I copied it correct. Okay, so let us just try to solve this one quick. Then you'll see the solutions. It's always easy. Okay, so I'll do our first. So what do we do? So let me just rewrite it. Okay, good. So the standard form you saw above, what we saw there is that the dy dx was standing alone. There was nothing disturbing it. So let us try to do that as our first step. But also another thing that you saw also that in this kind of the function, the dy dx, we see it to be standing alone on this side of the equality sign. So we can also do that. In fact, let us just try to do this together like that. So in one step, so we can just say dy over dx, we have divided with the x. So you will see in the next term here after equality sign. So therefore we have a minus because we are shifting things to the other side. So we here are having the brackets y squared plus 4 ln x. So it's a ln x. It's all over x, this x that we took from here. So it's all over x. How about we just say all over x here? What we see here, we nicely have a right hand side, and something special is happening on this right hand side. And what is it? We see that our right hand side is nicely in this form, where this could be our v of y is multiplying this side here, which is having x only, which therefore could be our u of x. So our right hand side is nicely telling us something special here, that our f of x y, which is the right hand side function, it seems that this function is nicely in a situation of being a product of two functions which are separated by multiplication. And this is very important. It's a very important thing that you want to see, because what this tells us is that we can be able to solve this differential equation using separation of variable method. But more into that, what we see here is that the term inside the bracket here, we have a term carrying a y squared. So on the two equations that we are solving, which maybe can confuse us when it comes into the test, the two equations which are linear first order differential and also the separation of variable method. The separation of variable method of the two methods, is the one that is able to solve nonlinear differentials. So the presence of this power 2 here must actually have already told, some, or say it might have indicated to some of us that really the integrating factor method will not apply here, but the method that will apply here is what is the separation of variables. Okay, so therefore we see that we have to apply the separation of variables here. So let's try to actually continue. Just apply the steps belonging to this technique and find the solution. Okay, so now we know the method, so let's just go ahead and separate. So therefore this will be 1 over y squared plus 4 dy, which is equal to minus ln x all over x dx here. I think when we started, we said the right hand side here where there is x, leave this side with x and some constant, and those constant, it could be some coefficient into these x variables. What we meant about that, for instance, look at this here. There is a minus sign here. This minus sign, you really don't have to bother yourself, following it through and say, therefore it's a minus on this other side. You don't have to take it to, just leave it on this side, on the side of the independent. Maybe if this was a minus 2, like that, then just leave this, just leave it on the other side. Don't actually waste your time. Just leave this coefficient on the other side. Then the next thing that we just have to do here, just have to integrate left with respect to y, with respect to x, and just apply the c here. Okay, as you can see, also we put the c also integration constant on the side of the x variable. Okay, so now what do we get? What we see here, you can use a formula sheet. The formula sheet will tell you this is 1 over a, and our a is 2 here. So it's a tan inverse y over 2, because it's a u over a, or f of x over a, according to the formula. So the side of the variable here is a y, and this term with the constant, this is a 2 squared, so 2 raised to power 2. Okay, so then this is equal to minus this integral. What do we see here? We are having a function and a derivative. So it's a ln of x and a 1 of x, and 1 of x is a derivative of a ln x. So what you can do here, you can use a u substitution, and when you use a u substitution, your answer that you will get will simply be ln x power 2 all over 2 plus a c. Okay, I'll just use a u substitution. In fact, maybe just so that we all are happy with it, what we did here is that we see that we have an integral ln x all over x dx. So we're having two functions. We have a function here which is a ln x. This function is multiplying a function 1 over x. Together these functions, they form this one integrand, right? So what we know is that we are not able to integrate two functions at once, just as we are not able also to differentiate two functions at once. So what you always try to hope for, or what you always try to do, is to get rid of one function so that we are left with one function to integrate. That one, if possible, we are always able to achieve that using differentiation, right? So if differentiation can assist, we always go for it. But there are instances where it fails, and what we do is that we try to use integration by parts. But what we say is that in this situation, differentiation will work here. So therefore, that will make our life very simple, because if it will work, then you can just go ahead and do some substitution and then target differentiation. So what substitution can we do here? We can let u is equal to ln x. So why we do that? Because we see that if we find a derivative, it's really just a du dx, really. We see that the derivative will be 1 over x, and then normally we'll just put a dx on this side. Okay, so from here we can just go back and continue, because we'll be able to eliminate one of these functions now. But what people like to do, they want to see things cancelling, so therefore they will go ahead and make dx subject to the equation, which will give us x du. Then we can now be able to go back to our problem and continue. This is equal to, therefore it's a u times 1 over x dx, which then is equal to a u times 1 over x. Let me just substitute. Dx is a x du. Right, we are moving slowly enough. Okay, so you can see then things are cancelling here. You can actually see that this 1 over x and the x, they will cancel each other. Then will leave us with one variable, which is a u, and also du, which we can actually conclude that the answer is u squared over 2. Right? Okay, so therefore I can say u is equal to ln, right? So this is why we have a ln squared over 2 there. Okay, perfect. So this is the general solution for this equation. Now we can go back into the problem. They give us some conditions, and they say when x is equal to 1, y is equal to 2. Okay, so let us come back and try to actually continue. We now have to get the particular solution. So therefore it's a 1 over 2 tan inverse y is 2 over 2. Therefore let us just say plus, already trying to make c subject of the equation. So it's a plus, so it's a ln. It seems it's a 1 here, so okay, seems we have nothing therefore yes, so it's over 2 equal to c. So therefore what we get is c is equal to, there is really nothing on this term of nothing, so therefore what we get now, we're getting that c is really just 1 over 2 tan inverse 1. You can check with your calculator what you get. You can have your calculator in radian mode, and then what you will get on this side here, you will get that c is equal to 0.393, which we can then conclude that the final solution that we are looking for is this one here over 2. Let us say plus, it's okay, we can just do that. Then it's a ln x power 2 all over 2 is equal to 6. Wonderful. Okay, so this is what we get. So quickly move on so that you don't have a longer recording, and some future recordings I also try to move fast, just I think now we're so relaxed. Okay, so number 2, which is the second one. Okay, let me bring it over here. So the second one is a y, so it's a plus y prime is equal to x y minus y prime. there are no conditions that are given here, so it means we just have to get the general solution. Okay, so what do we do? So we see a y prime. Of course, y prime is the same as a dy dx. It's just another way of writing. So they simply just use this prime notation here. So the dy dx, the Leibniz notation. So it's simply just they have the same meaning. So the standard form we have, there is only one dy dx. So therefore, let us try to put it together. Just put it on one side of equality sign where there is y prime. This therefore will be plus y prime. Then xy means it will be minus y here. So therefore are able to get a y prime, which is common here, leaving us with the y plus 1 equal to, also is common, leaving us with the x minus 1. So therefore we try to make it standard. Okay, so we're trying to get to the standard form here, so we must leave y prime standing alone without anything multiplying. So therefore we get y x minus 1 all over y plus 1, right? Very good. So next, what do you see here? What you see is that the variables have separated nicely on the right hand side. You can see that one. You can see the variables have separated nicely. Very nice. You can see. And then you also have the bracket with the x minus 1. Now you can see it's very nice. Something that happened here. It's very wonderful. So the next thing that we simply just have to do here, we really just have to separate this with equality sign. Okay, let me remove all of these dots, then we go ahead to separate. Okay, so let's go ahead. So therefore having y plus 1 all over y, let me break it into dy over dx, then is equal to x minus 1. Okay, so we do have this x variable with this differential here, so we have to remove it. So we therefore are getting 1 plus 1 over y dy, so is equal to x minus 1 dx here. So this we can put it in brackets. This dy it applies in both terms. We then just have to integrate. Then we put c on the side of the independent variable. So therefore, the solution that you get is a y. So it's a plus ln y here. So is equal to, so therefore it will be x squared over 2 minus dx plus c. Good. Okay, so there was no condition that you had given, so which therefore means our story ends here. This is the solution that they asked us to get. Okay, so this will be it. I think these two problems are enough. In our first recording, we also were moving very, very slow. We're so relaxed. I think the revision is done for the separation of variable method. So in the next recording, we will try to look into first order linear differential equations, which we will solve using integrating factor method. Okay.